All right, welcome to The Explainer. Today we're tackling something that sounds like it's pulled straight from a sci-fi movie, but is actually becoming a very real, high-stakes business plan, taking our data centers and moving them into outer space. Let's dive in.
So everything really kicks off with this one huge question. AI is growing at this absolutely explosive rate, but it's creating a problem that's very, very real and very much on the ground. We are literally running out of physical space and power for the giant server farms it needs. So where does all this stuff go when we just run out of Earth?
For the last couple of years, everyone thought the big bottleneck for AI was just getting enough advanced chips, GPUs and things like that. But that's not the whole story anymore. Now, the real bottleneck is the physical world. Building a new data center takes up massive amounts of land, and maybe even more importantly, it consumes a staggering amount of electricity. On a planet with limited resources, that whole model, well, it's just not going to work for long.
And that brings us to this pretty wild solution. Just move the data centers into orbit. What you're looking at here is the core economic bet. On the left, that red arrow shows the cost of doing this stuff on Earth, and it's always going up, right? Power gets more expensive, land gets more expensive. But on the right, that blue arrow shows the cost of doing it in space, and it is plummeting thanks to cheaper launches. The entire industry is basically in a race to find that crossover point, the exact moment where the blue line finally dips below the red one. And look, this is not just some crazy idea floating around. The biggest names in tech are already dropping massive bets on this. You've got Nvidia trying to get its GPUs into orbit, Google's got its own project, and the launch companies, they are all in. Jeff Bezos' Blue Origin wants to launch over 50,000 satellites. And then there's SpaceX. Elon Musk has filed to launch up to 1 million satellites. I mean, the scale of this is just, it's hard to even wrap your head around.
So what you've got to understand is that we're basically watching an orbital gold rush happen in real time. All these companies are rushing to file for specific orbital paths around the Earth, kind of like staking a claim on a piece of land, except it's a patch of sky. And companies like Nvidia and SpaceX, they're playing it smart. They're not just digging for gold. They're selling the pickaxes and the blue jeans. They provide the chips and the rockets, so they make money no matter who wins the race.
Now, when you hear space data center, I bet you probably picture something like this, right? A single, massive space station, kind of like the ISS, but just crammed full of servers, all humming away in orbit. It's the classic image from all the movies. But yeah, that's not how it's going to work. The reality is actually much, much smarter. A single giant station is a huge risk. It's tough to launch, a nightmare to assemble, and if one thing goes wrong, the whole thing is gone. So instead, the real plan is what's called a distributed data center, a huge swarm of thousands of smaller satellites. Each one is basically a single server, and they all talk to each other using lasers. It's way more resilient, you can scale it up, and it's a whole lot easier to get into space.
Okay, so how do we actually pull this off? Well, making this whole thing happen really boils down to solving these 3 fundamental challenges. You got to get the power, you got to get rid of the heat, and you got to launch the whole shebang into orbit. Let's break them down one by one, starting with power.
All right, first up, power. And this is where space has an insane advantage. Once you're above the atmosphere, there are no clouds. There's no night and day, not really. If you put these satellites in what's called a dawn-dusk orbit, basically right on the line between day and night on Earth, they can get 24/7 nonstop exposure to pure, unfiltered sunlight. It's pretty much an infinite source of free energy. And this right here shows you the key technology shift that makes it all possible. The old way for these precious one-off satellites was to use these super efficient but incredibly expensive gallium arsenide solar panels. But you can't do that if you're launching thousands of them. So the industry is actually going back to silicon-based panels, kind of like the ones on your roof, but with new tech that's making them more and more efficient. Perfect for the assembly line. All right, on to the next puzzle. And this one seems super simple at first. I mean, space is cold, right? Like absolute zero cold. So cooling a computer should be easy. But think about it. How do you actually cool something down in a total vacuum?
And here's the twist. It's super counterintuitive. Space is freezing cold, but you wouldn't feel chilly there. Why? Because there's no air or water to pull the heat away from your body. In a vacuum, the only way to get rid of heat is to radiate it away as infrared light. And to do that effectively, you need a gigantic surface area.
So just how massive are we talking? Well, to cool just 1 megawatt of computing power, which is a tiny little piece of a modern data center, you would need about 1,500 square meters of radiators. To put that in perspective, that's about a quarter of a soccer field. just for the cooling system, so this becomes a huge engineering problem. And that, of course, brings us to the final hurdle, the big one, the gravity problem. Every single chip, every solar panel, every square meter of that radiator has to be physically lifted out of Earth's really strong gravity well. For all of history, this has been the single most expensive part of doing anything in space. But this is where the entire game changes. Look at this timeline. The old space shuttle, it cost over $50,000 just to get 1 kilogram into orbit. Today, SpaceX's reusable Falcon 9 rocket has dropped that price all the way down to about $1,000. But the real key, the thing that makes this whole space data center idea actually work, is that last step, Starship. It promises to bring the cost down another 90% to just $100 per kilogram. That single innovation makes this whole crazy idea economically possible. So let's put some real numbers on this. Let's say you're building a small 1 megawatt data center. Over 5 years on Earth, that's going to run you about $54 million. Right now, to do the exact same thing in space, it would cost almost 3 times as much, about $158 million. You see, the AI chips cost the same, but the satellite itself, and especially the cost to launch it on today's rockets, is what makes it so expensive.
So yeah, this chart really drives the point home, right? The bar for Earth is down there at $54 million, while the space bar is way up there, almost triple the cost. But just remember those trend lines we talked about. The bar on the left, it's only going to get taller as land and power costs go up. And the bar on the right, it's about to get a whole lot shorter. And this all circles back to our main idea, that crossover point. This is a story about 2 lines on a graph moving in opposite directions. The cost of computing on Earth is going up, no way around it. And the cost of computing in space is coming down fast. The entire multi-billion-dollar race is just to figure out when. When do those 2 lines finally cross?
So what's the bottom line here? It's that this isn't science fiction anymore. We know we can do it. The real story here is about economics. The direction of the trend is set in stone. The only question left is when the costs finally cross over. And honestly, figuring that out is one of the biggest questions in technology and finance right now. It's no longer a question of if, it is absolutely a question of when.